controllers to tell it to change the dynamics to get the walking you want. Alright, so what we do in a very short summary, and by the way, this is work with Ryan. This is actually his first conference papers. It was his stuff that was presented at CDC. So he could come up and give this part of the talk if he wanted to right now. I even stole some of his slides, which professors do all the time, right? Steal your graduate student slides, right? And but they're good slides. So so we have 5 different control laws, and the main idea behind them is, like I said, we use passivity-based controllers along with local controllers. And what we really do is break down the domain structure based on whether you're fully or under-actuated. So if you've done control theory and dynamics, you'll understand there's this big differentiation between full and under-actuation. Okay? So the main point being of all this is that passive walking that we've seen, we can build controllers for those to achieve that passive walking on the fully actuated domains only. So basically what we need is to piece together that behavior on the under-actuated domains, and then we get walking, all in all. So let's talk about that. And I'm not going to go into great detail on all these controllers, but let's kind of give you a feel for the way controllers are constructed. So starting out, we do controlled symmetries. Now the controlled symmetries, the idea behind this actually worked by Swang and Bulow. The idea is that we have this passive walking down slopes. Okay? But what does down a slope mean? Right? It means gravity is pulling the walker at a certain angle. Right? So if you want walking on flat ground, what do? You rotate gravity. How do you rotate gravity? Well, you just shape the potential energy of the system. And now gravity is coming at a different angle. Right? Gravity is relative. So we can use control to shape the potential energy of the system. That's all I'm doing here. Based on some slope, gamma. Okay? And then we can get walking on flat ground. So doing this, we actually get nice walking, nice periodic walking. And this is in the case when we have only knees. It turns out that the ankle case, the ankles are important too, but basically, because we're fully actuated, you could pretend there are feet here and it's the same thing. Because we're actually actuating those nubs right now. And that's what feet are for, is to be able to actuate those nubs. But this is the walking you get on flat ground based on this mechanical properties of the system itself. And you see it actually looks pretty good for only, being straight leg walking with knees. Right? It's pretty nice walking. So we're going to build our controllers around this as being the canonical controller. Okay? Everything else we're going to do is little things to try to keep this happening when we have feet and we're under-actuated. Alright. So to do that, we do a couple other things. First, we do under-actuated control symmetries. All this means is when we're under-actuated, we can't completely shape the dynamics of the system. So what do? We shape the part of the dynamics that we have access to, based on what we did when we had full access to the system. So that's all we do here. It's sort of a partial shaping. Okay? What else do? We do spring dampers. If you're an engineer, spring dampers, you love them, right? They work great on everything. Okay, so you always have to throw spring dampers. This is a rule. Law of mechanical engineering. So we throw some spring dampers on. The last thing we do is actually the most interesting one, and something we're still playing around with a lot, is a lambda zeroing controller. Who's seen Lagrange multipliers? Remembers Lagrange multipliers. Okay, what do Lagrange multipliers tell you? They basically tell you the normal force to the ground. Okay? So when you're standing on the ground and your foot is pushing down, the Lagrange multipliers tell you how much is pushing up on your foot. Okay? So, in the part of the walking, the very important part of walking is, I shouldn't say it without a table in front of me. Every presentation I give, I do this. I walk all over the place, which is bad because my walking's not great. But here, so when you come up, I have weight on my heel right now, right? So there's a Lagrange multiplier. If I zero the weight on my heel to top it up, the Lagrange multiplier disappears. So what we can do with the robot to try to get that heel lift behavior is try to zero it. So you try to pop the heel. Okay? So that's the idea behind this controller. And finally, we have to make sure that our feet don't hit the ground. So basically, we just put some sort of virtual force field on the ground so that when your feet get close to the ground, your toe kind of lifts up and wants to stay away from it to prevent scuffing. So we put all these together on our system. Remember that we had all these discrete domains. And like I said, this structure is fundamentally important in designing controllers. Why? Because what you look like on each domain will dictate what controllers you use. Okay, not only that, but where you want to go on the next domain will also dictate what controllers you want to use. Okay? So we take our template of 5 controllers and we pick subsets of them that we want active on every domain. So in this case, what do we want? Well, we have full actuation, because our foot's flat. So we do our controlled symmetries, meaning maintaining that passive walking. We do spring dampers to prevent the system from rotating like crazy. And we do scuffing prevention to prevent the toe from hitting the ground. So once you have these templated controllers, you kind of throw them all together in a fairly obvious way. Okay, and then after that, what happens? Well, our knee strikes. Okay, now that our knee strikes, we do the same thing that we did before. But what else do we need? If we look at the next domain, our heel's off the ground. So what we need to do is get to this domain. So what do we need to do? We need to lift the heel. So what control do? We do the lambda zeroing control. And we top the heel. Right? So we start the control in this to get this behavior here. Right? So you just kind of do that. You sit down and go through, and if you understand all these basic things, you can kind of keep doing this. Keep doing it, keep doing it, keep doing it. Alright? So that's kind of the big picture stuff. If you do all that, you actually get walking, which is nice, because that's what we wanted. So here's what the limit cycle looks like for some of the angles. And basically, when I'm showing you limit cycles, by the way, I should explain what is a limit cycle. A limit cycle is a gate. Okay? Why do I keep showing these little loops? Because walking is symmetric. It's repeatable. Okay? So basically, if you achieve walking, you're going to return to the point when you start. So you're going to get a nice loop in the phase space of the system. Right? And it shows you have periodicity. So more importantly, though, and why I kind of skip all that stuff usually is, with walking, you always just want to show a movie. And that's where it's at. So here's the walking that we get. It's not bad. It's not great, it's not bad. It's probably some of the best walking to date, most human-like walking to date, but it's still not there, and I'm not happy with it yet, right? So at the end of the presentation, I'll show you the stuff we're doing now with human data, and that will convince you that there's a lot better walking that you can do, because you'll see that this looks like nothing compared to what we're getting now. But this was good, and it's only a year old, so it's not like this is, really old stuff here. But there's a lot of improvements we can obviously make. But equally important is, let's say, how do we go to three-dimensional walking? So the idea with three-dimensional walking is we really want to use this decoupling that humans sort of seem to have between their forward walking and their side-to-side walking. Okay? And so the way we're going to utilize this decoupling is geometric reduction. Okay, and I'll explain this a little bit, but I won't give you any math, because the math is kind of just confusing. So words are better in this case. And then basically this geometric reduction will allow us to decouple the behavior of the walking into its two-dimensional walking and its side-to-side motion. Okay? But that's only going to be true for certain initial conditions in the system. So then we do an input-output linearization controller to stabilize those initial conditions. Okay? Many of you have probably not seen input-output linearization. I teach nonlinear control next semester, and take it and you'll see input-output linearization. Because this is a staple of all nonlinear control, all modern nonlinear control, is this idea. And I'll probably give you a little verbal description of it, but I don't show you the math. All right, so we've achieved this two-dimensional walking. It looks good. Let's make it three-dimensional walking. What do? Well, we're going to start out by taking a three-dimensional biped, and we're going to do this sagittal restriction that I talked about to get to a two-dimensional biped. Okay? And once we do that, we can do our sagittal control lock. By that, I mean everything I just showed you. Okay? And then we get two-dimensional walking. That looks pretty good. So what's the next thing we do? We want to get this decoupling. So our first control, it takes the system, and it shapes the energy of the system so that we have a system that's amendable to reduction. And then reduction allows us to directly relate the behavior of the full order system and the reduced system. Okay, so let me try to explain this a little bit. Reduction, has anybody seen geometric reduction? No, probably not. So this is actually very popular in physics. It was pioneered by Marsden, who unfortunately just passed away recently, but he was very much living at this intersection between mathematics and engineering and physics. And the idea here is there are certain symmetries in systems. Okay? So if you have a double pendulum, a pendulum in three-dimensional space, as you rotate the pendulum around the z-axis, nothing really changes with the system. Right? Gravity is still pulling the same way. Everything is the same pretty much. Okay? As opposed to if you take a pendulum and you lift it up and down, the way gravity is applied to the system is changing. Okay? So geometric reduction says if you have symmetries like this in the system, you can essentially get rid of those variables and reduce the system to a lower dimensional system with that behavior. Okay? So in the case of this three-dimensional pendulum, you can actually make it a two-dimensional pendulum by understanding that there's those rotational symmetries.